a fellow of the Royal Society, and he was also awarded a prize by at the Queen's birthday this year, which I'm not sure, they have royalty in the UK as well, so apparently you can get a prize at this birthday, which I understand was a great honor, although I don't understand quite what it was. But he has also told me that he has sat next to David Attenborough at the dinner. Okay, so that's more impressive. He also has told me that he has 2 weeks, or he has had now before coming here, he has done 2 weeks of Duolingo. So therefore, any questions afterwards can be taken in English or Norwegian. With that, it's a great pleasure and honor to have you here. We're very happy to have you here, and we're looking forward to your talk.
Okay. Thank you, Victus. Okay. Can you hear me okay? Yeah? That's good. Thank you, Victus. Well, I had a wonderful weekend. Victus was showing me the landscapes of Norway, and absolutely fantastic weather. I hadn't realized she was taking notes on everything I said for her speech today, but it's a real pleasure to be here. And likewise for me, I think it's the largest audience that I've spoken to in 2 years. So it's a real pleasure to have people here and not names on a screen, which has been most of the last 2 years. Okay, so today I'm going to be talking about the metabolism of the Earth as a whole. And this is a talk that that covers many disciplines. I know many of the audience here are probably biologists in some form. There's elements of biology in here, but there's also elements of history and energy and sustainability and various things all mixed together into this basic story. Probably I would say that the most important and urgent question of our century is how can we learn to live on a finite planet? The lesson of the 20th century, I think, was realizing our planet was finite. Starting with the CO2 accumulation curve, we realized the atmosphere didn't go on forever, that if we poured waste into the atmosphere, it would accumulate over time. Realizing our fisheries are depleting, our other factors are depleting. And I think that the challenge of the 21st century is to take that knowledge and insight from the 20th century and come up with a pathway through the 21st century that allows for a vibrant humanity on a finite planet. Now, this is a huge challenge, and the answers are not necessarily easy. With lots of metrics that we could use, we could look at the temperature of the atmosphere, we can look at the number of species on Earth, and there are lots of really important and valuable ways of trying to assess the state of the planet so we know how we're doing and how we can change the trajectory. What I'm going to do here in this talk is focus on a different metric, one that isn't used generally, and just to see whether it's just one way of looking at the planet, but to see whether it gives some insights, some different perspectives that the other metrics don't give. And this metric is metabolism. And I define metabolism as the flow of complex energy through biological organisms. So it's different from, say, pure thermodynamic energy, heat, emissions, and etc. It's complex energy. Most cases, chemical energy, but not always, as we'll see. And that's the broader definition of metabolism that I'm talking about. And we all may have come across metabolism in terms of biometabolism, our individual metabolism, but all living organisms have a metabolism. This tree has a metabolism, or plants do, or fungi do, and that means that there's complex energy flowing through all of these organisms. And we know ultimately, in most ecosystems, almost all ecosystems, this is captured sunshine, captured by photosynthesis, that then ends up cascading through an ecosystem. And a lot of my own research, which I'm not going to talk so much about today, but those of you coming to the departmental seminar tomorrow, I'll talk a bit more about that, is around measuring these flows of carbon, in particular nutrients in systems, and how it varies. There's a student of mine at our site near Oxford, Whiteham Woods, measuring photosynthesis of a leaf by putting there's a chamber there, we close it, and over a minute we measure the rate at which carbon dioxide concentration declines in that chamber, and from that we can work out the rate of photosynthesis of that single leaf. if we do this over multiple leaves at different seasons and have a model, we can scale up to estimate the total photosynthesis of that tree. If we do multiple trees, we can estimate that forest and that woodland. And this is the sort of work that my team has been doing in multiple places, particularly in tropical rainforest regions over the last 15 years, where we measure these productivity, these flows of carbon and nutrients in different ecosystems, and try and understand how they're affected by climate, by disturbance, by biogeography, and all these factors in all the major tropical continents. And so we've created this network called the Global Ecosystems Monitoring Network, or GEM, and then you can see a list of the sites there where we're measuring ecosystem traits and energy flows and a variety of things, mainly in the tropics, but we venture into other areas as well. And so that's one approach. There are also other approaches. One is to use micrometeorological approaches, where you build a tower and you have this instrument, which is called an eddy covariance approach, where the sensor is, you measure the turbulent fluctuations of the wind speed up and down, and at the same time you measure the concentration of carbon dioxide in that same packet of air. And if you do this multiple times a second and carry on over the day, you can see the flow of carbon dioxide in and out of the forest. And if you do that over the year, you can see the seasons, the winter, the summer, and the interannual variability. And from that you can, often it's used in terms of carbon fluxes, to say this is what the carbon balance is, and we focus a lot on carbon, but I think you can also think of it as flows of energy in a system. And so much of this sort of work is focused in terms of carbon because of the interest in climate change, but the conversion from carbon to energy at first level is quite straightforward. This is a very simplified textbook equation for photosynthesis, but essentially it's carbon dioxide and water and energy from the sun forming carbohydrates and releasing oxygen. And there's a standard free energy, about 40 kilojoules of energy for each gram of carbon assimilated. And so if we've got data on carbon productivity, we can convert to energy very easily. And so to quote a famous Scottish writer, the sun shines not only on us, but in us. That we are all captured sunshine cascading through ecosystems, and that is the fundamental metabolism that drives all of us. And in terms of units, energy is in joules, energy flow per second is in watts. So just to calibrate you in some of the numbers that I'll talk about, this is an old-fashioned tungsten light bulb. Typically it's about 60 watts, so that's 60 joules of energy being consumed by that light bulb every second. A human body, most of you here are around 100, 120 watts, so about 2 light bulbs of energy are burning in you all the time in terms of chemical energy that supports your life support systems. So that's the measurements that we can do at the local level, and ultimately we want to scale up from the site to the ecosystem and ultimately to the biosphere. And that's where we use remote sensing approaches, satellite approaches, where we look at the properties of simplest level, the greenness, but some of the work we now do is use different wavelengths of light to understand the relationship between the site and the productivity and then scale to a larger level. And we come up with maps like this. So this is an example where individual sites have been scaled up through a model and satellite data to estimate the metabolism of the land surface, the total photosynthesis. And on the right you see it's in terms of units or grams of carbon per meter squared per year, but we can also sum up and convert into energy units. So the total amount of energy flow through the land biosphere, we know with some confidence, it's around 150 terawatts, or 150 million watts overall. And you can see patterns that we understand quite well. The highest productivity is in the wet tropical regions, where there's a year-long growing season. When you get to drier regions like the Sahara or the higher latitudes with long winters, that productivity tails off. And we can do similar things in the oceans. with parallel approaches of field studies plus satellite data, and we see this pattern of global ocean productivity driven by different factors. Water doesn't matter so much, temperature doesn't matter so much, it's the availability of nutrients either running off continents or being welled up from the deep ocean that determine the overall pattern of ocean productivity. And the total metabolism of the oceans is similar to that of land, but a little bit lower. So land was 150, ocean is around 120 terawatts of energy. So this is one way of looking at energy flow. One of the advantages of being in the geography department is that there's lots of people who think cool things about maps and think about how can we map things. And I had a colleague a few years ago called Ben Hennig, who's now at Reykjavik, and he was an expert in cartograms and using these area-based ways of thinking about often economic and social data. So we sat down over coffee one day and thought, well, let's try and convert some of this biological data into cartograms as well. It takes a little bit of nudging to work out how to do it. And then this is the same figure that I showed 2 slides ago in conventional geographic representation, but here is a cartogram where the size of a pixel represents the metabolism, the productivity overall. So you see what's happened overall, that the deserts have shrunk to nothing, the big wet tropical regions have bulged out, the higher latitudes are shrinking overall. And we can do this for every month of the year. So if you do it in January, you can see Norway. Where's Norway gone? I thought Britain was bad, but Norway's shrunk to insignificance there. Most of you in Bergen in January can probably sympathize with that biologically. So in January, we live on a land surface. We live on a tropical planet. Most of the biological activity in January on Earth is hugely in the tropics. And if you go to July, Norway looks a bit better. We've had the great greening of the northern hemisphere, and the long daylight as well means that overall productivity is pretty high in the northern hemisphere in July. And the tropics still maintain their year-long productivity. So we can couple those together for month by month and end up with this, which is as a working with geographers can be great sometimes. And you get this pulsing heartbeat of the land metabolism over the year, and you can see that overall seasonal cycle. I'll stop that now. The first time I showed this, my postdoc said she had a headache for a day afterwards, so I won't expose it for too long. And then we come up with this overall global pattern. So that covers how we can think about the metabolism of the biosphere geographically now. We understand that pretty well through field measurements and satellite scaling. We can also think about how this metabolism got here. How has it changed over Earth history? How has it evolved? And this is a little bit of speculation here, but it broadly matches what we know about the planetary metabolism. So this talk is quite big picture. Now we're going to one of the last billion years of metabolism. So if we go back a billion years, 1,000 million years, we see until for most of that period and for much longer, planetary metabolism was entirely marine. Life evolved in the oceans, and this is I think on retrospect the numbers are probably too high for this period. It's probably less than that in the early part of this graph. And there were periods where it shut down even further. So there were snowball Earth episodes where the Earth almost entirely froze over, and perhaps the tropical oceans, either there were open water or there was just slush of some form with very limited productivity. The productivity of the planet collapsed to almost zero at that period. But coming out of the snowball Earth, there was perhaps a surge in ocean productivity, and over time marine productivity has increased gradually with various biological innovations, some retreats at time overall, but there's been a gradual increase in marine productivity. But in terms of overall planetary metabolism, the next big innovation was the colonization of the land surface by living organisms, which occurred around 400 million years ago. And so this was an interesting challenge for life because marine productivity has some limits. There's plenty of water, but light is limited to the surface areas, with a strong attenuation of light and energy supply in the surface. And on land, you had this abundant energy source of light falling on all this land surface, but there were fundamental constraints, and particularly water. How do you hold on to get access water? How do you hold on to water and use water? And it took a while for life to innovate the solution for that, which involved plants, vascular tissues, storage mechanisms, and, which occurred around 400 million years ago, symbiosis with fungi as well that enabled that. And that's when we start seeing this access to a previously inaccessible energy source, which is all the sunlight falling on the land surface. And that led to a surge in overall planet metabolism, a doubling of planetary metabolism overall, and maybe some periods of retreat during ice ages, and then overall an increase in metabolism, probably peaking in the late Cretaceous or the Paleocene, Eocene period of hot house Earth, where temperatures were substantially warmer than the present. There was rainforest-like vegetation extending to the latitudes, probably the latitudes of Scandinavia or Alaska overall. And so it was an extremely productive, probably the highest productivity that the Earth has seen. And since around 40 million years ago, there's been an overall cooling and drying of the Earth, probably linked to the rise of the Himalayas and other mountain ranges and the increased drawdown of carbon dioxide through weathering, causing the overall cooling of the planet and the drying of the planet as a consequence. So that we're at the end on this timescale of a long period of cooling and decreasing land surface metabolism, but still substantially higher than it would have been in deeper time. So I'll come back to this figure later. But much of my focus so far has been on the biological metabolism of Earth. But what I'm going to focus on now is on a slightly different question, which is human metabolism. How much energy is flowing through human societies? And the parallel image, the one I showed before, is from the 1970s, is this one from the last decade, which I think has become one of the iconic images of our human-dominated planetary age. This image of lights at night, which is quite mesmerizing in some ways, but also captures, I think, our sustainability challenge, that we're seeing all of these changes happening on a thin layer of atmosphere that's just a few kilometers thick, and a thin layer of biosphere that's just a few meters thick, and a thin layer of oceans as well. So what is the limit of this compared to the biological function in these thin layers? So why focus on this metabolic approach? Well, I think energy flow is one metric of describing our ability to change the world around us. How much energy flows through societies compared to through the biosphere tells us how much ability there is in those societies to transform the biosphere around us. The physicist's definition of energy is the ability to do work. And so the more energy a system has, the more work it is able to do. So can we compare the metabolism, the energy flowing through humanity, with the metabolism of the rest of the biosphere? And a key thing also is to recognize that this human metabolism is embedded within the planetary metabolism, that it isn't as humans are somehow apart from nature. This metabolism arose from within the planetary metabolism, and how does it relate to that wider nurturing planetary metabolism? So the concept, so organisms, as I've described, have a biological metabolism, and the concept I'm going to introduce now is either the extended metabolism or what we call the social metabolism, that includes not only the biological energy in human societies, but the energy embodied in our transport systems, our material consumption, our infrastructure, and bringing all of that together to compare that to biological metabolism. And so I'll look at the short history of social metabolism over the last 10,000 years. And if you go back 10,000 years, well, everybody on Earth was some form of hunter-gatherer, gathering plant materials and hunting or fishing for some materials. And based on, but as I already described, the basic biological metabolism then is very similar to what we have now, around 120 watts, around 2 light bulbs. All societies, even hunter-gatherer societies, have a social metabolism. There's costs in cooking food, for example, embedded in the materials that are used, and that ranges between 100 and 1,000 watts, but on average it's around 300 watts as a typical extended metabolism of a hunter-gatherer society. And one of the challenges of the hunter-gatherer lifestyle is that in most cases it can only support very low population densities, that you're essentially relying on what you can find from natural ecosystems, and most natural ecosystems aren't that freely giving of their resources, and that limits population density. There are a few exceptions. If you have a rich fishery offshore, you can have higher, more dense populations, but on average population densities are in the range of around 1 person every 10 square kilometers in a hunter-gatherer society. So if we multiply the per person metabolism of 300 by the population density of 0.1, we come up with the social metabolism per square kilometer of the surface, and that's around 30 watts per square kilometer. So one low energy light bulb of energy, of human social energy per square kilometer is what hunter-gatherer societies were doing in terms of energy. And let's compare that to the environment in which we originated as a species, the East African savannas, and the types of measurements that I described at the start enable us to estimate that the biological metabolism of a savanna is around 30 megawatts, 30 million watts per square kilometer, and therefore this early human hunter-gatherer social metabolism is around 0.0001% of the energy flowing through that savanna, the biological energy flowing through that savanna. And so that overall shows why humans had limited impacts. They did have impacts. They changed the fire regimes of these savannas. They probably hunted some species to extinction or changes in abundance at least. But overall, they were relatively modest compared to the changes that were to come later in human history. So this hunter-gatherer mode of life began to change around 10,000 years ago with the advent of the Neolithic Revolution, the advent of agricultural societies. And one way to think of agriculture is that it's the colonization of ecosystems. So rather than the ecosystem doing what it does and we take whatever resources we can get from that ecosystem, we convert the ecosystem so that its primary function is to provide resources to human societies. So that's one way of framing agricultural societies, and that's been the mode that's enabled human civilization and villages, then cities and towns to develop. And there are various innovations that could be done over time, but one of the challenges of agriculture is that ultimately it's largely a land-based system, and there can be innovations, certainly over time, but ultimately it gets constrained by the amount of land available to provide energy to human societies. And I'll show an example of how that plays out in human history in a bit. And so this is the primary mode of human energy consumption, whether it's food or raw materials or actual combustion came from agricultural systems. And that began to change. So if we look at the peak of this mode before it began to change around the 17th century, and so this is calculations for Central Europe around the 17th century, and you see a society there where there's some natural elements to the ecosystem, but large parts of that landscape have been modified to be primarily for human use. The metabolism of these societies is much greater, the extended metabolism than the hunter-gatherers. Now it's around 2,000 watts per square meter as per person. And the population densities can be much higher now. There's much more resources there. It also allows for stratification of society into more concentration of societies into towns and cities, for example, or into denser villages. Supports a much higher population density. And this probably is the reason why agricultural societies win out over hunter-gatherers. It's not that there's a lot of evidence that the transition to agriculture actually decreased individuals' quality of life. The life expectancy, the decrease, the disease burdens, social inequality increased. But overall, you could support much higher populations with an agricultural mode, so they tended to outcompete non-agricultural societies in the same landscape. And so if you multiply those two numbers together, you come up with a per unit area metabolism of around 80 kilowatts, a lot more than before, per square kilometre. And if you compare that to a temperate forest, which would have been the natural ecosystem in this area, this is about 5% of the natural ecosystem metabolism. And when you have these percentages, it's interesting to reflect what's the right level of percentage to aim for. 5% can feel quite small, but I would say interpret this as this is a society that's having a substantial impact on natural processes. This is a measurable increase in the total amount of energy in societies compared to the natural ecosystems around them. And we see in this painting that these are quite substantially altered ecosystems. And this can be done more generally over time. This is a book by a historian, Ian Morris, with a terrible title, but actually it was a very interesting analysis and a data-rich title there, which looked at societies in Eurasia. So this is everywhere from the British Isles to Japan, and looked at the biological and historical data, trying to estimate the per capita energy use of those societies that I converted here into metabolism through a few assumptions. So this is material energy use, so it's not just energy used for combustion or heating, it's in the food systems, etc. And overall, you see this pattern with and the west here is everything from Iran westward, so includes the Middle East, the origins of the earliest settlements in Eurasian civilization, and the east is Greater China, Japan, Southeast Asia, and that area. And so overall, you see that the West, in this sense, had a slight head start with civilizations in Mesopotamia and Egypt, and then the spread of that into the Mediterranean and beyond. And the East was soon after in this transition to agriculture, but that the head start lasted for much of the Holocene. And then I'll zoom in on this period later, but you see this general rise across Eurasia, and this is per person metabolism, so the amount of resource consumption per person. And we see something quite interesting in the data for the last 2,000 years, where you see a flattening out of this rise over time. And in the West, peaking around the time of the Roman Empire or the Han Dynasty in China. And then about 1,000 years ago, we see that the East has generally the per capita metabolism seems to be higher than the West at the time of the Song Dynasty. But overall, in both cases, things are flat. And overall metabolism of societies increased because population was still increasing. But what was happening is that innovations in efficiency were translating into population increases rather than into per capita consumption changes. And if metabolism is some metric of quality of life of the average person, things weren't changing much from the Roman Empire until 1700 in terms of the resources that were available to individual people. So things, and one reason to speculate about this is that it could be this issue around this metabolism is entirely land-based, or almost entirely land-based. And these societies were naturally hitting some sort of limit or boundary where the amount of available land for resources had been, all the good land was used. And you could have, and there were minor increments in efficiency, but they were always compensated for by increments in population. There was not more land available for more energy supply as a whole, for Eurasia as a whole, to do that. And we seem to be hitting what essentially could be called a planetary boundary in some ways, or a regional boundary in terms of this mode of energy and material use. So this began to change around 1750, and you can guess why it began to change, which is the transition to a different mode of energy that wasn't land-based and started shifting towards fossil fuels overall. And one way of thinking about this is that what happened in around 1750 is that human society discovered a time machine. And that up until then, almost all our energy came from the present-day biosphere. Either this year or the last decade or so of biosphere production was the entire energy supply system. And by energy, I don't just mean, again, there's this food and everything and all those forms of energy. And what happened with this transition is that we started, rather than using the energy of the present day biosphere, we started using the energy of the deep time biosphere. So the photosynthesis of 100 million years ago or 200 million years ago was powering contemporary societies. So it's this use of this development of this time machine that enabled this surge in per capita energy consumption. And so we see that in the patterns that we see in per capita metabolism in the data, initially in the West, and then soon after in the East, we see this surge that this time machine enabled. And what happened here is that society had access to a previously unavailable source of energy, which is the energy of the past. And so in some ways, there's some analogy to what happened with the colonization of life on land, where a large but previously inaccessible source of energy became available to life on Earth. There was a geographical expansion when life colonized land, and there was a temporal expansion with the Industrial Revolution, that we started colonizing the energy of the past to provide resources for the present. And so this is a zoomed in on that period, but also if we look on the timescale of the last 12,000 years, you see the scale of this transition of what happened overall. And clearly in biology or in physics, you can't have graphs that go like this for very long. Something has to change in that system overall. And I think this is one of the challenges that we face. How do we transition this into, whether by force or by choice, into something that stop this graph just keep on going up off the chart. But yeah, this is the mode where we've all grown up, where a generation or a few generations of society have grown up with this assumption of constantly increasing per capita metabolism. And the challenge of this century is to work out what we do next. So one other way of visualizing that is here. This is an animation that shows it's carbon dioxide emissions, but rather than thinking about it in terms of carbon dioxide emissions, see this as the birth of the industrial metabolism. So as you can see, it all started around 1750 in this small island in Western Eurasia that starts going blue. By about 1820, you're starting seeing the rest of Europe starting to light up and get brighter and brighter in its industrial metabolism. By 1860, the eastern side of North America. By about 1900, you'll see Japan starting to light up. And analysis of this industrial metabolism can explain a lot of politics and resources and who was powerful at different times as well. So you go to the 1950s, the Great Acceleration it's called. Suddenly you see large parts, after the Second World War, large parts of the planet light up with this industrial metabolism. And this is the near present day now in terms of the emergence of this industrial metabolism. So let's turn to a current day industrial society. I'll focus on the UK, but it's probably quite a few parallels to here in Norway. And the social metabolism of the average person in the UK is now around 8,000 watts, about 4 times greater than the 17th century agricultural society. The population density is much greater. Now we can, this abundance of energy enables people to concentrate in cities, to have transport and infrastructure networks, so food from not only other parts of the country, but other parts of the planet can be brought in efficiently into cities. The population densities are much higher. And so we know, we can estimate that the natural metabolism of the ecosystems that would have occurred in the UK would have been about 360 gigawatts. And the social metabolism of UK society now is 500 gigawatts. So it's greater than the biological metabolism of that landscape. How is this possible? 2 main reasons. One is a lot of the metabolism isn't dependent on the biosphere. It's dependent on the past biosphere, or more recently in other sources of energy. And also a large part of that metabolism are imported from other parts of the planet, from the tropics and other regions, that enables this to work at a national scale. So it's 140% of ecosystem metabolism. So I'll just to briefly divert a little back into ecology for a moment before jumping back in. And ecology tends to be shy of having laws. The physicists like laws. The ecologists tend to be very suspicious of laws overall. One thing that sometimes claims, one entity that sometimes claims to be a law is Clibber's law. And this is about metabolism. And it's about how metabolism scales with body mass in any group of organisms. And broadly, in any single group, you tend to, this is on logarithmic scales, on a logarithmic scale, you tend to get a reasonable straight line relationship. So in the normal unit scale, this is a power law overall. And the slope of that isn't 1-to-1. It's more like something like 3/4. And there's a whole field of ecology that argues about why it's 3/4 or if it is 3/4 or not. I won't get into the details of that. But essentially, what it tells us is that per unit mass, larger organisms have a lower metabolism than smaller organisms. So a kilogram of elephant has a lower metabolism than a kilogram of mouse. But you get this broad pattern. So in this social metabolism context, we can ask an interesting question. So this is the metabolism of different organisms, different mammals as a function of mass there. So the question we can ask is, well, this is just our biological metabolism, but I've just been talking about how we're more than biological metabolism, we're a huge social metabolism. So the question I can ask now is, well, if we take into account our social metabolism, how big an animal would we have to be to have the same biological metabolism? So how big are we really when we take into account our extended metabolism? And if we do that, you can see the hunter-gatherer is a bit bigger than our biological human. The medieval agriculturalist is a bit like a rhino. The average industrial mean is like a large elephant, more maybe like a mammoth, maybe, in terms of their metabolism, 15 tons. And then I always like to pick on the North Americans. The average North American is about twice that in terms of their overall equivalent mass. So the average industrial human has the resource consumption of a 15-ton primate. And in North America, this increases up to 30 tons. Such primates exist only in fiction. And so if you want to understand why we have a huge impact on the planet, one reason to think about it is to see each of us as a 15-ton King Kong roaming the landscape. So imagine Bergen full of, I don't know, however many 100,000 King Kongs roaming the landscape. And you can see why we have an impact on the biosphere, on the environment around us. And so, okay, so I've given you a metabolic perspective, and hopefully it's triggered some interesting perspectives on human history and planet. But also, is this practical in any sense? Is there an application to this? And this is something that's open to debate, but it can be an interesting way of thinking about the world. But does it have a practical use? But I'll give us one example of how we've explored this. And this is again in the context of the UK, where I had a student a few years ago who just loved pulling together data. That was his obsession. So we worked together and we just did a very detailed, more spatial analysis for the UK of the breakdown of what makes up the average UK person's social metabolism and how is it spread spatially. And so I'm sure Norway's pretty close in many of these aspects. So they've compared to sort of more semi-urban or peri-urban environments. So it's a very efficient way of having a large number of people on the planet. And we can also do some other interesting things. So for England alone, we also had lots of social deprivation data. So where there were interviews for each district about different metrics of social deprivation. And we were able to plot deprivation against metabolism. And broadly, we'd expect some sort of negative correlation, that areas that tended to have higher metabolism tended to be more prosperous overall, and therefore tended to have less deprivation. And broadly, you see that pattern. But what's interesting is that the variance is so great overall, and the variance is more interesting than the overall pattern. So there are areas on the top right here, which are red on the map, which have quite high metabolism, but also high deprivation. So that metabolism isn't solving deprivation issues, it's improving the quality of life of many people, at least. And then you've got areas here that have relatively low metabolism and relatively low deprivation. And some of them, maybe not scalable. We see Oxford does quite well there. That's a university city with relatively prosperous students going around in bicycles. Maybe that's a model that can be applied more widely, but there are also particularities to Oxford that make that difficult to scale. But maybe generally we can look at ways of bringing societies down here. And we look spatially, we see areas like the southwest of England that has a lot of very poor infrastructure, transport infrastructure. So there's much more personal consumption of transport because there isn't a railway system that's extensive, for example. So there may be interventions there that can bring down metabolism. But it shows you just one example of how you can start actually thinking about things like the trade-offs between human welfare and metabolism by looking at this spatial data in more detail. So let's go to the planetary scale now and look at the metabolism of the planet as a whole. And I'll just focus on the land biosphere because most of our activities at a metabolic scale are on land. Certainly we have a huge effect on fisheries and aspects of the ocean. But in terms of primary production, it's land where we're affecting the primary production of the biosphere. So if we calculate the hunter-gatherer population 10,000 years ago and the total metabolism, that was, this is crude, just doing some estimates of productivity in Norway. Probably the total amount of energy flowing through human society globally 10,000 years ago was about the biological energy flowing through Bergen municipality now, the energy flowing through the forests and the ecosystems in an area, 3 times the area of Bergen, the municipality of Bergen. If we go to about 1700, the total amount of energy flowing through agricultural societies worldwide is about 3 times the biological energy of Norway in terms of the productivity of Norwegian ecosystems. And what I've tried to do here is this is a bit crude at these smaller scales. The size of this circle compared to the size of the planet there is some roughly area-based metric of the size of human metabolism compared to the size of land biosphere metabolism. If we go to around now, the total human metabolism is around 25 terawatts, which is 17% of biosphere metabolism, roughly the metabolism of Amazonia, of the Amazon rainforest. And it's interesting again to think about what's the right level here. 100% clearly is not a desirable level. When some people see this number, that they're amazed at how important Amazonia is in terms of biological activities. It's equivalent to all of human energetic activity on the planet. Whereas others see this as they're equivalent to the Amazon forest biome as a civilization in our energy footprint. And if we go into the future, if we go for a mid-range UNDP projection for the middle of the century, the energy flow through human society would be around 32% of biosphere energy. And you can see this red circle is getting larger and larger compared to the size of the planet there, on an area basis. If we go to global China, where everybody on the planet had the same per capita metabolism of the average Chinese person today, we're looking at 40% of the biosphere. And if we all go for the American dream and go for the global USA, the total energy consumption metabolism of the planet is 120% of the land biosphere overall. And I think this encapsulates the challenge that we face, that the mode of metabolism that's kept us going through the last few centuries is hitting something new, which is planetary boundaries. The fact that previously we could always rely on getting resources from other parts of the planet or various other innovations, but the challenge we face now is the business as usual will take us to a point where our metabolism is larger than the life support systems of the planet can bear and maintain. And that fundamentally, I think, describes the challenge that we face this century. So let's take this on a deep time perspective. as well. So you've seen this, and I pointed out that the transition to life on land was a substantial, probably the biggest change in planetary metabolism in Earth history. So if we look if we consider humans as embedded in the biosphere, as part of the biosphere, not something separate from it, the mid-range projection for 2050 would be comparable in some ways to the transition of life on land in terms of significance, in terms of energy flow through the Earth system. And if you go for this global North America scenario, it's huge. It's compared to the transitions in Earth system. And so we often hear about changes now being significant on the timescale of the last 10,000 years or human history. But some of the changes in the energetics of the planet are significant on the timescale of all Earth history. Significant geological events that ramify on the scale of the entire history of the planet. And so one way of framing this has been this concept of Anthropocene. Maybe compared to the previous figure, this is perhaps an ambitious term, but that suggests that we're in a new geological age which replaces the Holocene, in which humans have been a major influence on climate and the environment. You could argue, based on the previous graph, that perhaps we're in the Anthropozoic or a more deeper change in the nature of Earth history. And this describes this idea of the Anthropocene, and this is a review I wrote a few years ago, and this blue line just is some metric of increasing human influence on the planet, and highlighted are some of the debates about when the Anthropocene began, whether it's the Industrial Revolution, the conquest of the Americas by Europeans, or with most of the consensus arguing now for around the mid-20th century, this great acceleration after the Second World War, but some arguing that the Anthropocene is not yet here. It happens when we hit planetary boundaries such as 2 degrees of warming or something in the near future. But this broad framing of this line going up to planetary boundaries is the overall concept. And what I propose here, I suppose, is that metabolism provides a metric for that y-axis, so some way that this is, from being a qualitative thing, it actually is one way of measuring this increasing human impact on the planet overall, and the fact that it's approaching planetary metabolism. And there are lots of other metrics that come as a consequence of this. This is a nice paper from a couple of years ago that shows the total. This metabolism overall has created mass, particularly waste and concrete and other components and gravels. That's equivalent to the mass of the entire biosphere. It's just one metric of human impacts on the planet. And I would argue that many of the environmental issues that we think about are ultimately driven by the challenge of this large metabolism. So whether it's deforestation, whether it's over-harvesting of resources, whether it's pollution in the atmosphere causing climate change, or issues around waste, ultimately they're driven by the size of and the quality of this metabolism. So when we think about this orange circle as the human metabolism embedded within the biosphere, in practice, it isn't a single smooth surface. It's a many thousand tentacled creature embedded in various aspects of the biosphere. How does it interact with the biosphere? This hungry metabolism depletes resources, harvests resources. It pumps waste, metabolic waste, which causes climate change, ocean acidification, plastics, etc. And also it occupies physical space that reduces availability of space for other species on the planet, and all the consequences that are there. And so when we're trying to think about reducing the impacts of this metabolism on the biosphere, that one thing that we can think about is the quantity of this metabolism, how big it is, and how we can limit that it can't grow indefinitely till it swamps the entire planet. But the other thing we can also think about is the quality. So the more of this metabolism that either draws its resources externally or it circulates its resources, the less it draws on the biosphere for its resources, the less it pumps waste into the biosphere. So the more circular this metabolism becomes, the less it has an impact on the wider biosphere. And so our challenge is not only to think about limiting the quantity of the metabolism, but also improving the quality of this metabolism so it's more circular. And there's various ways that can be done. And this is just one example of how those two could work out. This is just simply power generation in the UK, which shows that overall power generation has begun to decline, but also a larger fraction of it is coming from non-fossil fuel sources, and that's half of what it used to be just a decade ago. So this is an example of how you can think about limiting the quantity, but also begin to think about changing the quality. So in this case, through renewable or non-fossil fuel energy sources. Now, all this metabolism, you may come across thinking, oh, this is some sort of a thing that is a negative thing, clearly has lots of challenges, lots of problems we need to think through. But that increased metabolism in many cases has improved human livelihoods in so many ways. In the past, in Europe, but nowadays in much of the world, where the chances of your children living to adulthood, the chances of receiving health care, of education, of the things that we take for granted in a prosperous world, are transitions that have occurred because of increasing per capita metabolism in many parts of the world. So the challenge we have is how we reconcile this improvement of the human condition with a finite planet. And part of it is important to remember is that this metabolism is unevenly distributed. We often, when we talk about the Anthropocene, we often end up talking about we, the human species, as a collective. But if you look at many metrics, and here's just one metric, which is cumulative carbon dioxide emissions, it's very unevenly distributed. It's a small fraction of human society that predominates in terms of the metabolic impacts on the planet. So in this case, in terms of carbon dioxide emissions, the existing climate change that we're experiencing now, you see Europe and the US and North America account for half of the existing climate change that we experience now. And so one way of thinking about the big challenge, I think, is reconciling improving human welfare with a finite planet. And my colleague in Oxford, Kate Raworth, is an economist, thinks a lot about these, and she modified this idea of planetary boundaries into this idea of the donut, the planetary donut, where our challenge is to live within an ecological ceiling while having sufficient social foundation that basic human needs are met, and where they're not being met, there's an improvement in those human needs. And so the challenge is to both identify this safe and just space and to navigate into that space. And this is a broad conceptual idea, but more recently she's been working with cities and others to try and work on this as a practical tool for thinking about navigating and staying within an ecological ceiling. And another way that this is framed in her work is that traditionally we've had an economic model of societies and nature as an externality from which we draw resources and which to pump waste, and we might want to bring that externality into the economic model, into the economic framing. But a different way of thinking about this, which I think is essential now, is to see that the economy is embedded within society and all the wider needs society has beyond economic activity alone, and that society is embedded within the living earth. And that makes sense to a lot of us, but it's not the way our social models, our economic development models are built at the moment as a framework. So in this framework, what I've described to some extent is the social metabolism describes that society, the planetary metabolism describes the biosphere in which our global society is embedded. And so I showed maybe at the scale of nations we can do this sort of metric of looking at comparing the social metabolism with the biological metabolism, and that can help us and think through this challenge. And maybe something equivalent can begin to be done as one of the tools to think through the sustainability challenge of how we can live as this active civilization on a vibrant but finite planet that is the origin of us all and sustains us all to this day. So, thank you.
much, Yadvinder. And it's not very often that you sort of get these new perspectives of how to think about things. And so the first times I saw these maps and I saw these ways of representing, I thought it was very, very fascinating. And it's so fun to hear you talk about it. So thank you for that. We will take questions. And so if anybody has any questions, please raise your hands and I will try to find you. Yeah. I'll run around.
Thanks for the great talk. I had a further question about renewables. You were hinting at them as being a solution. And I wondered, can renewables just level off that spike that you were showing, or have they got the potential to go even beyond that spike, given the amount of energy, for example, in terms of solar that's landing on the Earth?
Yeah, no, that's a very good question, because I think one of the perhaps perspectives that comes from using metabolism as a framing is that we realize that the problem is more multifaceted than, say, climate change alone. Now we could imagine, let's say we come up with hydrogen fusion, that we can have all the energy we want with zero environmental impact of the energy production itself overall. And that abundance of energy would probably amplify many of the other aspects of our impact on the planet overall, because many of our activities are still energetically limited overall. So certainly I think just switching energy systems alone would solve the climate change problem. But I think the metabolic problem is a more fundamental underlying problem that has lots of other different facets. So part of the challenge, I think, it has to be to find a boundary to metabolism, and then within that, try and turn that metabolism to be a cleaner, a more renewable metabolism.
Any other questions? Yes,
you noted that the human consumption is about 8,000 watts global average now. Do you know how that compares to the global warming? Because all the energy we use is ending up as heat. Does it all show up in the budget for global warming, or is that completely driven by changes in insulation and?
Yeah, I haven't got the numbers, but I suspect the latter. I think the actual thermal effect, all our human activity is negligible to the planetary thermal balance overall, whereas the greenhouse gas effect, which changes the fraction of that energy that's trapped in the lower atmosphere, is the dominant effect there overall. I think it'd be interesting to calculate, but I suspect that once you calculate it up, even though it's a huge biological metabolism, it's tiny compared to the non-biological energy flow in the system, which is affected by the CO2.
That's possibly a slight, tiny bit of good news then. Any other questions?
I have
Yeah.
Very interesting, and I accidentally remember the heat transport just west of here, so that's about 150 terawatts, just the flow of ocean water northwards across the Greenland Stockholm Ridge.
Oh, interesting. Okay, that's equivalent.
50 terawatts, so I think that's comparable to the
planetary biological.
Right? So the energy flow in the Earth system is a lot larger. On a personal level, I understand. I mean, if you wanted to go voluntarily down in metabolism, I understand it's the calories we eat, and it's the house heating, right, and it's the transportation. But were you also able to look into the numbers for buying electronics and all those other consumption? So what should you do if you wanted to bring down your personal metabolism? Apart from not eating too much and
I guess well, I think we could have a look at that breakdown in the UK. If I go back to that.
I feel like we're talking about the extended diet here now. That doesn't only.
Yeah, you can see this is the components of a UK metabolism overall. So you can see that like personal transport, cars as opposed to public transport is about 14%. So if you don't use cars, that's 14% reduction on average in your metabolism. Gas use, so turning down your thermostat a little bit is one example there. If you're just thinking about the personal thing you can do. A key point, I think these personal things are important to think about. But in a lot of climate change debate, I tend to think we must think about the structural change as more important. It's very easy to get distracted by how can I be a better person individually, whereas actually we need our societies to be better societies and to think through the infrastructure, the energy supply systems and those things overall. But you can see this gives you, if you want to think about your personal footprint, you can see how it roughly splits out into different components there.
So electronics, for example, or is
Yeah.
it fairly small?
You can see it's pretty small. It would be in maybe in household goods and services there overall. So it's compared to the amount of energy going into transport and heating, for example, it's quite a small amount of metabolic energy.
We need a global metabolic
Yeah.
gym.
I mean, in some ways, just one example of that is with a pandemic that when global society almost shut down, the global planetary energy consumption dropped by 7% or 8%. It was, even though we talk a lot about traveling and all the footprints of that, but ultimately much of our metabolism is about heating homes and transport systems domestically rather than those issues. And that pandemic was a good case study on what needs to nudge to actually affect the energy consumption overall.
Other questions? Not here.
Thank you for a great perspective on many things in scale. I wanted to ask, I saw the donut model being applied to investigate local impacts of cities or regions, or even internally. I think it's allowed to use in companies. Do you have any plans of applying your model on for governments or,
Right.
or companies?
Yeah, that's an interesting question. I think, firstly, I don't think this is just one interesting metric. So I don't think it's the answer in any sense. But I think it could be one way of adding a quantitative element to some of these donuts type approaches to thinking about it. So we are talking actually just the scale of Oxford, for example, of just trying this out as working out a donut model for Oxford that not only looks at the domestic, the Oxford-based footprint, but also all the embedded consumption comes in from around the world to support Oxford. So then this metabolic approach is one way of thinking about it. And the planetary boundaries is another approach. I guess one nice thing about metabolism is that it sort of brings everything down to one axis, which has some limitations, but it also perhaps in some ways is easier to work with than having multiple axes to think through.
On the second round.
Yes. Sorry, I realize I have an opportunity here now to talk to a plant scientist that knows about metabolism. There are two questions I've always wondered about.
Okay, right.
The first is how many leaves are there on a mature oak tree? Second, you might know because you've calculated and summed it up and modeled it and stuff. And the second, do trees exercise?
Do trees exercise? Okay. The first one, I don't know the answer, but I know somebody who does, who's actually calculated it, and I can't remember the answer, but it's a surprisingly large number. Do trees exercise? Probably exercise is a conscious thing you do to improve your metabolic performance. So I don't know, I suppose not already. I can't really think of the consciousness part of it, I suppose.
You could say some trees run faster than others.
Yes, yeah, but do they exercise?
So I was wondering about agriculture. So you showed like these 120 watts basically that we biologically use, or that's our metabolism. So that would be kind of the output of
Yes.
Agriculture, because that's what we eat, right? And on the other hand, agriculture is part of the social metabolism. So in a sense, that would be some kind of amplification factor of our own metabolism.
Yes.
And I wonder, how has that historically changed? So how much kind of energy you need in the social metabolism to get out 120 watts, and in how much that can actually be reduced in the future. So for example, we have all these ways of, I don't know, electrifying things, using the consumption of fossil fuel
Yes.
But with agriculture, I guess, there must be more limitations than just switching to nuclear and renewables.
Yes, yeah. No, that's a good question. I think I wouldn't know the current numbers, but I think for the 1700, then the number I had for metabolism there, about 2,000 watts, is probably a reasonable estimate of the scaling factor, at least for a 17th century society, because most of that metabolism ultimately was to feed people and to keep them warm as well. So roughly it's a factor of 20 times, maybe 10 to 20 to compare wider metabolism to support the 100 watts of human metabolism. In terms of the second question about what can be done about that, yeah, it's an interesting question. I don't know whether the energetic efficiency can come in a modern agricultural system. Clearly, you can change the quality of the metabolism. So, as you said, not using fossil fuels as the primary as source of energy for the food system, reducing the transport element of the food system or the heating element of the food system where it's possible to minimize the size of that metabolism. But yeah, it's not an area of my expertise to know exactly with the food system how, but I'm sure there are areas in there that the energy footprint can be reduced as well.
Okay, I think you were first. Also, it is this side of the rooster. My metabolism is doing quite well now.
Good, yeah.
Yes, so relating to how much is enough in terms of social metabolism to sustain a decent life. Several scholars have linked the number of, let's say, dollars of consumption in a given society to different indices of well-being and welfare. And that means like not GDP, but some different indices that we use for that.
Yes.
Are you aware of any attempts to relate social metabolism and any of these indices on human welfare and happiness? And secondly, whether that could inform some policymakers on the question how much is enough to sustain?
Yeah, that's an interesting question. It's an obvious thing to do, and I'm not aware of any studies that have started to look at that. In some ways, you could argue that a comparison with social deprivation, if that's a measure of happiness just as a society, is perhaps one example where you can start doing that within a particular country. And you could look across countries as well. And I think a granular level of social metabolism data hasn't really been done across many countries because the type of data that are required haven't been assembled in many cases to do that. But in principle, I think some sort of first order estimate could be done in a similar way. I think it gets more interesting once you get more granular. I think the whole country one, it masks a few people with a very high metabolism, with others with a low one. But once you get in within a society and look at how people's quality of life is affected by the metabolism and where the compensation points are there. So I guess to some extent, this is what we're beginning to do here to some extent. How can we, if you take the x-axis as some measure of societal happiness, we wanted low deprivation. So and you can see that overall, we're not seeing any sort of plateauing, but we are seeing a huge amount of variance within regions about that relationship between metabolism and deprivation. It isn't a simple condensed relationship, which I think offers lots of potential. Could this society all be at the lower envelope of these curves? Could we actually be all down here if the right policy and infrastructure decisions are made? Or if the wrong decisions are made, will we end up at the top end of this with, overall?
Okay, we have a final question, I think, over here before we wrap up.
Okay, so my question depends a little bit on what's on your slides. If you go back to the pre-industrial.
Pre-industrial, yep.
Yeah. If I got the numbers right, yeah. So
This one, yep.
exactly, the comparison there. Because you said, so you estimated extended metabolism of 300 watts.
Yep.
Right? And then the population density of 0.1.
Yep.
And then in the next slide, like the extended metabolism increased by an order of magnitude. Is that right?
You mean for the agricultural society?
Yeah, agricultural.
Yep. So yeah, about 2,000 watts per person, yeah.
Yeah, is that right? An order of magnitude.
Yeah, per person.
The density that, technically supports.
Yes, it's much higher.
Technically supported is much higher.
Yes.
So do you have, is that, do you have an explanation for that? What the difference is?
Yeah, so
Because in the last estimate for present day, it was also more or less proportional.
yeah. Well, I'm not sure if it was proportional because the modern day was even higher, about 300 watts per square meter. So, so here we've got like a roughly an 8-fold increase in per person, and orders of magnitude increase in the population density. And that's simply because this is the overall agricultural societies are a very efficient way of getting resources from a fixed area of land compared to natural ecosystems where you're harvesting berries or hunting for a few animals. So the overall energy able to be extracted from ecosystems is orders of magnitude higher in this agricultural system. And I guess the way it played through is part of that goes through into improving the per person energy consumption, but most of it goes through into increasing population density. This is how it played out in history overall. So given the increased resources, how much of that goes into per capita increase versus population density? In this case, the history shows that most of it went into increased population density and a modest amount into per capita. And again, actually, that's roughly what the industrial society also did. That you had a 4-fold increase in the per capita consumption, but again, a 8-fold increase in the population density overall. So it's not quite as extreme. But it seems overall, over history, when societies have had to be able to extract more energy from the biosphere, on historical timescales, that tended to go into population increase and less into per capita consumption.
It's a fascinating topic. Thank you for all the interesting questions. We're going to wrap up now. Thank you again to Yadvinder for coming here and for telling us giving us this fascinating new perspective on sort of how to think about both the biosphere and how it works, and also our footprint on it. And some quite worrying both graphs and time machines and all these new pictures that I have in my head. We have some presents for you. Jan says that I should give you.
All right, great, sir. Thank you.
I don't know what it is, but it's probably very
Thank you. Very good.
And then thank you everybody for showing up.
Thank you. Well, thanks for a nice Bergen mug.
It's great to have physical meetings happening again.
Yes.